Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to Calculus Class. We will solve another example that involves deformation principle. So we want to integrate a function f of z equal to 1 over z minus z naught, where the z naught is a complex number, number within a closed curve C, and we want to integrate over this C. So I want to integrate my 1 over z minus z naught over this C. So like suppose I have a point z naught which is lying within a closed curve C, and I want to integrate my 1 over z minus z naught over this curve, right? So because deformation principle allows me to consider any curve over this z naught, so if I'm given with a curve whose equation I don't know, then I can consider on my own another equation. So for my convenience I will consider a circle of radius r. So let me consider a radius of a circle of radius r which is centered at z. Let me consider this z of t to be z naught plus r e to the iota t, where t is running between 0 to 2 pi. So this is equation of circle which is uh, centered at z naught and has the radius r. So what I need more? I need the derivative of z of t, which is r iota e to the iota t. What more I need? I need f of z of t. So my z of t is 1 over z minus z naught. So in my case, if I insert this value over here, so I will have z naught plus r e to the iota t minus z naught, right? Which is basically equal to 1 over r e to the iota t. So now by applying the integral formula for the complex integrals, which is given by a to b, in this case 0 to 2 pi, and f of z of t, which is this guy over here, 1 over r e to the iota t. So the formula that I am using is this one. So I should show you the formula that I am using. So this one is the formula for solving the complex integral when parameterization is given. F of z of t times z prime of t dt. If you don't know, please watch my other videos on complex integration introduction. So f of z contour integration. Okay. So what? Yeah. So like f of z of t is inserted, and then I will substitute the value of z prime of t, which is r iota e to the iota t dt. So this is basically minus over here. So this should also be the minus. So this gets cancelled with this, r gets cancelled with it, and 0 to 2 pi I dt, which is basically 2 pi times iota. So the integral is 2 pi times iota. Now let's generalize this concept more. Instead of considering f of z equal to 1 over z minus z naught, now let's consider 1 over z minus z naught power n, right? Where n is some positive integer. So n is some positive integer, right? So if it is 0, what should be, for 0 we can see it's a constant function, and constant function is continuous, so Cauchy-Goursat theorem allows us to conclude something. But now let's say n is from z positive, and also n is not 1, because for n is equal to 1 we have seen the result, right? So since my z naught is within a curve C, so the same assumption as we had above, so we can also consider a circle z of t equal to z naught plus r times e to the iota t over this. And what is going to be my derivative? So it is going to be r e to the iota t time iota, and my t is running between 0 to 2 pi. What more I need? I need f of z of t, which is going to be equal to 1 over z is z naught plus r e to the iota t minus z naught, and this can be simplified to get 1 over r power n times e to the iota n t, right? So let's now substitute these values in the formula, and the formula of the integral when we are given with the parameterization is given by a to b f of z of t times derivative of z dt. So a to b is 0 to 2 pi, and f of z of t is 1 over r power n times e to the iota nt, and what more is the z prime of t, which is r times iota e to the iota t dt. We can simplify this. So r is constant, so we can take it outside, 1 over r power n minus 1, and then 0 to 2 pi, and this becomes e to the iota t common n minus 1 dt, and then we can apply the integration formula r power n minus 1. So this is exponential integration, which is iota t n minus 1 uh, divide by divide by iota times n minus 1 and 0 to 2 pi. So this was integral as we do in the calculus 1 sense. So it is 1 over iota times n minus 1 times r power n minus 1 times e to the iota t times n minus 1, and my limits are 0 to 2 pi, right? Okay, so when I substitute the values of the limits, 1 over iota times n minus 1 r power n minus 1, so of course n is not 1, because if n is 1 then this becomes, so for n is equal to 1 we have already the result. So when we substitute iota times t, so this is basically n minus 1, so t is 2 pi, so 2 pi is in place of t, and when we put 0 it is 1 basically, right? Now I will work out this quantity, what this is equal to. So e to the 2 pi n minus 1 times iota, right? But we know that e to the iota theta is equal to cos theta, which means cos of n minus 1 times 2 pi plus iota times sine of n minus 1 times 2 pi. So you know this is multiple of 2 pi, right? So this should be 0, and multiple of 2 pi, when we compute cosine of multiple of 2 pi, is equal to 1. So when we substitute this value 1 over here, what we will be left with is the integral over this curve of this function is equal to 1 minus 1 over iota times n minus 1 r power n minus 1, which is basically 0. So we can say that this particular integral, uh, 1 over z minus z naught power n dz is 0 when n is not 1, and it is equal to 2 pi I when n is equal to 1. So n is not 1 of course, but n was from the z positive so far, like so like I can write it in the piecewise form, that this integral of 1 over z minus z naught power n dz is equal to 2 pi I when n is 1 and 0 when n is not 1. Of course n is from positive integers, but what if n is negative integer? If n is from negative integers, that means n is equal to some minus k, where k is a positive integer, right? So in that case I can write this integral 1 over z minus z naught power minus k dz, which is equal to integral z minus z naught power k dz. But now this becomes a polynomial function. So we are in the assumptions of the, and this polynomial function is analytic on all the domains. So we can apply the Cauchy-Goursat theorem for simply connected domains, the very first version, and it gives me 0. So like I can remove this n from z positive, it can also be from negative integers. So now I will formalize it, that I want to integrate 1 over z minus z naught power n dz. This should be equal to 2 pi I when n is 1 and it is 0 when n is not 1, and n can be any integer other than 1, right? Okay, so what are some of the other consequences? So if you take z naught to be 0, then this integral 1 over z power n dz is also satisfying this. So it is going to be over some closed contour which is surrounding 0, is going to 2 pi I when n is not 0 1, and it is 0 when n is 1, right? You also need to keep in head that we are assuming that this z naught uh, is a point in such a way that the contour over which we want to integrate is surrounding this. So this was one of the application of deformation principle, or you can say that Cauchy-Goursat theorem. Much more to come.